Alright, cool. Good evening, everybody. Today I'm going to be talking about minimax rates for homology inference. So what we're going to work with is an unsupervised learning problem. So you're given samples x1 through xn which are drawn IID from some manifold embedded in a Euclidean space, possibly with noise added. So what you should imagine is you have something like the figure on the left. There's some surface and what you're seeing is a noisy sample from it. And what you'd like to do is to infer some sort of coarse topological properties of the underlying manifold. I'll be a little bit more formal about what I mean by that in a few slides, but for now probably the best way to think about this is via analogy to clustering. So clustering somehow is asking this question: what are the connected components of your underlying data manifold? And we're asking a sort of different question, which is, can you also distinguish, say, a torus from a sphere? So in some sense, both of them have exactly one connected component, but when I give you samples from a torus, there's a hole in the middle, and you'd like to be able to discover something like that. So here's another example. It's from a paper by Partha Neogi, Steve Smil, and Shmuel Weinberger. So the figure shows 3 clusters, and what you should imagine is your underlying data manifold is just 3 points, and what you're seeing is samples with Gaussian noise added. And so this is what you typically think of when I say Gaussian mixture models and clustering in that sense. So here's another picture of 3 clusters, but it's not quite the same, and it's not drawn from a mixture of Gaussians. But if I asked you what the difference was, you would probably say that 2 of these clusters have additional structure, and if I asked you what that structure was, you would say 2 of them have holes in them. All right? And so the topological properties, what I'm going to be talking about, are somehow some kind of summary of this kind of properties of your underlying data manifold. Okay, so here's another sort of toy application that motivates topology. So topology in some sense is this loose notion of geometry, which is geometry inherently sort of rigid, and the task is to mine molecular dynamics trajectories. So the video shows a molecular dynamics trajectory. So what you're seeing is essentially a simulation of a protein in a solvent, and it's going to wiggle around for some time as it walks along an energy landscape, and when it reaches some sort of minimum, it folds. And what you'd like to do is to mine this in the sense that without having a biologist watch a long video of this sort, you'd like to be able to figure out when something interesting happens. And so one way to define interesting is to say when the protein folds, it forms some sort of loops and things like that, and so its topology changes. So when it wiggles around, its geometry is changing, but that's not very interesting, and what you'd like to identify is when its topology changes. And so there are many, many more applications of this sort of topological data analysis, and tomorrow's invited talk happens to be about understanding the cosmic web using this sort of techniques. Okay, so now let me start to be a little bit more formal about what I mean by topological properties. So what I mean is topological invariants, and what these are essentially anything that's invariant under a homeomorphism. So what it is just a continuous map which has a continuous inverse. So in some sense, if I take your data manifold and continuously deform it, then I don't change any of its topological properties. Right? So here's an illustration. A filled coffee cup and a donut are homeomorphic. That is, you can continuously deform one into the other. And what this means essentially is that they have the same summary or the same topological properties. Right? So in this talk and throughout our paper, we focus on a particular invariant, which is the homology groups. And there's 2 primary reasons for doing this. The first one is that they're rich in the sense that they capture interesting topological information. So in the beginning, I showed you this example of 2 clusters with holes in them. And this sort of information is captured by these homology groups. And the second, probably more fundamental reason is that they're easy to compute. And in some sense, they're the only topological invariant that people know how to compute. And there's a lot of packages out there that do this. All right. So now I'm going to start explaining what exactly I mean by the homology of a manifold. And the way I'm going to do it is sort of non-standard, but I'll do it by reducing the task of understanding the homology to computations on some graph-like object. And so I'll do it in 2 stages. I'll take the homology of a manifold related to the homology of a collection of balls. And then what I'll do is explain how to calculate the homology of this collection via a graph-like object. Okay, so here's the first step. You take your data manifold and imagine replacing it by a dense collection of points on the manifolds with tiny balls around them. This object is still continuous and it's not graph-like anymore, not yet at least. So here's the here's what you should imagine. This is a manifold. I take some dense sampling and I put balls around them, right? And a well-known fact is that if the manifold is smooth in a certain way and the balls are small enough, then the homology of the manifold is exactly the same as the homology of this union. And the way to intuitively understand this is because you can take these balls and squish them back onto the manifold in a continuous way. So in some sense, the manifold and this union are homeomorphic. Okay, so now the question becomes, how do you compute the homology of these unions of balls? And this proceeds via these things known as simplicial complexes. So given a collection of points and some radius epsilon, you can build this thing called a check complex. And the way to do this is to treat the points, which are the centers of the balls, as vertices. If the epsilon balls around any 2 points, any 2 vertices intersect, then you draw an edge. And so far it looks like a graph, but you go a little bit further. If the epsilon balls around 3 vertices have a common point of intersection, then you draw a triangle, and so on. So here's an illustration. There are 5 points. Here's the balls around them. So this is the union of balls. So this is sort of the underlying manifold. And one thing you should observe is that there's a hole in the center of this, and this is something that you'd like to capture. But let me proceed. So if I take the epsilon balls, some of them intersect, and these are the edges that are formed. What you'll also see is that the 3 points on the top have balls which have one common point in intersection, and so there's a triangle in this graph as well. And another important theorem is that without any assumptions, the homology of the check complex is always equal to the homology of this union of balls. And so now all I have to do is tell you how to calculate this homology of a check complex. Just a refresher, the simplicial complex is made up of simplices. So a 0 simplex is vertices, 1 simplex is an edge, 2 simplices are triangles, 3 simplices are tetrahedra, and so on. So there are important structures to keep in mind on the simplicial complex. So think about collections of p simplices. For a second, think of 1 simplices, which are just edges. So one fundamental structure is that of cycles or loops. And so what you'll see is that manifold that I drew has three non-equivalent cycles. So there's one little cycle, one big cycle, and one that goes through these 3 vertices. And another important concept is that of boundary cycles. So what you should think of is filled-in cycles. So boundary cycles are cycles which are the boundary of some higher order simplex. So in this case, the only higher order simplex is a triangle, and there's one cycle that's the boundary of this. And what all of this does for you is that it induces equivalence classes of cycles. So I consider 2 cycles to be equivalent if they differ by a boundary cycle. So in this example, the little black cycle and the big black cycle are equivalent because they only differ by the little red cycle, and which is a boundary cycle. So what I've defined for you is just a class of cycles which are called equivalence classes. And that's it. We're essentially done. So the groups of equivalence classes of the cycles are called the homology groups of the manifold. And so the ranks of these groups are called the Betti number. So they're essentially counting how many equivalence classes are there. And so if you return back to the example, what you'll see is that there are 3 cycles, but there's only one non-trivial equivalence class of cycles. And this is capturing the fact that your manifold has exactly one hole. And that was what we started out trying to get at. Okay, so now let me return back to the original problem. This is the original problem. You're given samples from a manifold, and what you'd like to do is learn or infer the homology of the manifold. And so now I'm going to introduce both upper and lower bounds, and the way this typically proceeds is to give you an upper bound. I'll show you an estimator and analyze its sample complexity. To give you a lower bound, I'll show you that no estimator can do much better in terms of sample complexity. All right, so let me introduce some assumptions. So the first one is a sampling assumption. Before I add noise to the points, the density has to be bounded away from 0 everywhere on the manifold. So what this means is that you should be able to see, in some sense, every part of your manifold. And the second assumption is the first part is just standard, it's compact, it's d-dimensional, it's Riemannian. And the most important assumption is that it has a condition number that's at least tau. And this condition number is an important quantity. It controls the curvature of the manifold. It also controls how near 2 distinct components of the manifold can be. So it ensures some sort of separation for you. So it's, let me just define the condition number formally. It's the largest distance tau such that every point within the condition number from the manifold has a unique projection back onto the manifold. So if you think of a circle, every point in space except the center of the circle has a unique projection to the circle. And so its condition number is exactly its radius. And another way to understand this condition number is to imagine growing a tubular region around the manifold, and you stop when it hits itself. So that's what the figure is meant to illustrate. And this is a very important parameter. It's a single parameter that cleanly controls the hardness of this problem. All right, so now let me talk a little bit about noise models. I'm only going to discuss the noiseless case in this talk, or mostly discuss that. So here are the noise models. The first case is the noiseless case. Here you see samples which are directly on the manifold. The second case is that of clutter noise. So what you see is a mixture model. You either get a sample from the manifold or you get a sample somewhere around it. And I mean, it can be anywhere around it essentially. The third case is a tubular noise model. So here you get noise which is essentially in some thin region around the manifold. And the fourth, probably most interesting case is additive. So I draw a sample from the manifold and I add noise in some way. So I can add Gaussian noise or I can add any other kind of noise. The only restriction is that the Fourier transform of the distribution of the noise has to be bounded away from zero, and this is sort of a technical thing. Okay, so now what we're going to try to do is this style of analysis called minimax analysis. So what we're going to ask is, what is the risk of the best possible estimator on the worst, hardest possible distribution in your class, where the risk is defined to be the probability given n samples. So this is the probability under the product measure of getting the homology wrong. So there are two important quantities that you can read off this. The first one is the sample complexity. The sample complexity is just the minimum number of samples you need so that with probability at least 1 minus delta you recover the homology correctly. And another one is sort of important quantity is the resolution. So what this says is, what is the smallest condition number of a manifold whose homology you can learn given n samples. So this is sort of like a feature size. So this is the smallest feature size that you can track given n samples. So here's a very nice theorem from Partha-Neogi, Steve Smith, and Shimon Weinberger. What it says is essentially this. If I give you n samples in a region, in a very thin region around the manifold, and if these samples are very dense on the manifold, then just taking a union of balls around these points has the correct homology, and you can compute this via the standard check complex trick that I just showed you. And so now what this does is that it moves all the randomness into the second part. So the only thing you need to analyze is when are the samples sufficiently dense on the manifold. And so in the noiseless case, for example, you can read off the following statement. It says that with probability at least 1 minus delta, around 1 over tau to the little d, where little d is the dimension of the manifold, samples are enough. And so what this means is that the sample complexity is completely independent of the ambient dimension. All right. So here's their strategy for upper bounds. In the noiseless case, you get a bunch of points, you take a union of balls, compute the homology of the resulting check complex. So one thing that you can easily generalize this to is when the samples are concentrated around your manifold, but there's some noise around it. And so in this case, you denoise the data, and the way to do this is you take a kernel density estimate and you throw away points in regions of low density. And then you take a union of balls around the points that survive, and you can show that this has the right homology. And so when the samples are concentrated around the manifold, denoising is in some sense easy, and you will always get rates independent of B. So the other sort of more interesting case is when the samples are not concentrated around the manifold, but you know something about the distribution of the noise. And in this case, the strategy we follow is to do this thing which is known as deconvolution. And so the idea is that you're going to try to estimate the noiseless density directly from the noisy samples. And so let me just tell you a little bit more about what deconvolution is. So the first observation is that the noisy distribution is a convolution. It's just a convolution because the noise is additive. It's a convolution between the noiseless density and the density of the noise. The second observation is that a kernel density estimate is also a convolution. It's a convolution of your kernel with your empirical distribution. And so now it's easy to see that if you wanted to directly estimate the distribution of P in given samples from Q, you would use a kernel density estimate, but you would modify it in a certain way, and that's what's given by this equation, and that's the only take home. So deconvolution essentially says modify the kernel in some way and then do a density estimate. So in our case, it turns out that the distribution you're trying to estimate is singular because it's supported on a lower dimensional structure, so you need a little bit more care, and then you can derive some rates out of this. And so most of the details are in our paper. Okay, so now let me just briefly talk about lower bounds. So the intuition to producing a lower bound for this sort of problem is that you want to find two manifolds that have different homology, but which induce distributions that are hard to tell apart given a small number of samples. So this is sort of the general intuition of trying to reduce estimation to testing. And so more formally, you have something which is called Lecam's lemma. In our case, what it translates to is this. If I can produce any two manifolds that have different homology, and they have associated distributions Q1 and Q2, then the minimax risk is lower bounded by something which depends on their total variation in the following way. And so what I would like to do as a strategy is to produce two manifolds with different homology whose induced distributions are close in total variation. Right? And this construction is very easy to explain in one dimension in the noiseless case. So as I said before, you want manifolds that are in some sense geometrically close but topologically different. So in one dimension, your first thought would be take an interval and take an interval with a hole. That doesn't quite work because it has a boundary and so on, so you just smooth it out at the edges and you get two manifolds that look like this. And it turns out that you can do the calculation, and what it gives you is a lower bound that looks like 1 over tau to the little d times log 1 over delta, which exactly matches the Niogi-Smale upper bound up to a factor of log 1 over tau to the d. Okay, and I'm about to conclude. So this is a summary of our contributions. The paper has a lot more details for the minimax bounds for all of the noise models that I just discussed. And hopefully at a high level, what I've convinced you of is that homology or topological data analysis is a useful thing, and you can capture rich topological information about your data given a small number of random samples. Thank you.
Any questions? Yes.
So you're probably having some applications also in mind. So what I was asking myself during the talk, any applications are the manifolds algebraic?
I'm not sure I understand the question. What do you mean by are the manifolds algebraic?
Are they given as a zero set of some polynomial equations?
So the only application that I'm sort of vaguely interested in is the one that they're going to talk about tomorrow, which is on this cosmic web. So essentially you have a bunch of points which correspond to galaxies, and then you get edges in a certain way, and you're asking questions about that. So it's not algebraic, at least the ones I've seen.
No, he was phrasing it before. Okay. Yeah.
Okay, with respect to noise removal,
Yeah, so
they have an incredible rich amount of information.
yeah, so I mean, I guess I sort of dodged the issue of how do you pick all these parameters that I'm introducing, so the epsilons and the noise thresholds and so on. And so probably the right way to do it is via persistence. So you look at these barcodes and then try to do something without having to actually commit to parameter choices. So we've been looking at this from a different perspective, which is how do you give sort of confidence intervals for barcodes or for persistence diagrams. And so that's sort of a more statistical view of that whole thing. But yeah.
So you can go ahead now.
Yes, so I wanted to ask a little bit something similar also regarding the parameters. And I'm wondering if you have a certain set of samples. There are a lot of topologies that this might correspond to. So if you say you infer the topology, the optimal thing would be a probabilistic answer. So
So, okay, so here there's a manifold. I mean, the way it's set up, there's only one right answer. There's a manifold and it has a certain condition number, and the guarantee is based on this unknown condition number. And so if you take a union of balls, which depends on this unknown parameter, then you get the right answer. So, I mean, really, I'm dodging very heavily all the questions of how do you pick parameters and this sort of thing.
But this condition number is a very strong assumption that in reality, you don't know if your data has this condition number.
But then sort of, I mean, that's what the lower bound should convince you, that if you don't know the condition number and you don't have any other control over smoothness, then you're sunk, because you do need the sample complexity does inherently depend on this parameter.
Okay, so thank you very much.